Thank you for watching this video. My name is Yuisudo from Honda Research Institute, Japan. I'm going to talk about our research entitled Streaming Automatic Speech Recognition with Reblocking Processing based on Integrated Voice Activity Detection. In recent years, automatic speech recognition has been actively researched, and many practical applications have been deployed. In fact, we have been also developing an ASR system for the hearing impaired, and we believe that end-to-end ASR systems are promising technology. However, most streaming ASR methods assume that the input speech is appropriately segmented into short utterances in advance. So many ASR systems usually use external voice activity detectors in a cascaded manner, which increases system complexity. Additionally, errors generated in the external VAD cause performance degradation of ASR due to the error accumulation. Therefore, we propose to integrate voice activity detection into ASR to reduce system complexity and error accumulation. Firstly, I will review some related works on streaming ASR. Typical streaming ASR is a unidirectional RNN-based method. This is a straightforward streaming ASR using recurrent neural networks, but in general, its performance is relatively poor compared to state-of-the-art transformer-based methods. Another method of streaming ASR system involves blockwise processing, which efficiently restricts the length of the attention window in transformer. In this paper, we focus on blockwise streaming transformer based on CTC attention, which retains the context of long utterances across the block by using an additional context embedding vector that inherits previous encoder states. However, if the speech is improperly segmented for each complete utterance, the inherited context is discarded, resulting in performance degradation. On the other hand, many VAD methods have been proposed, such as zero crossing, MLP, RNN-based methods, and so on. Although VAD is computationally inexpensive, increase the number of modules in ASR system increases its complexity. And also errors generated in the external VAD causes performance degradation due to the error accumulation. Several attempts have been made to integrate voice activity detection into ASR. For example, an integrated VAD method using CTC-based end-to-end ASR model was proposed. In this method, blank labels can be regarded as non-voice segments. However, it lacked optimal performance because it was not trained for VAD. So we propose to integrate voice activity detection branch into a streaming ASR model. The VAD and ASR models share the encoder to avoid increase in the number of parameters. And we also propose a novel reblocking technique to realize appropriate voice activity detection with block processing-based streaming ASR. This page shows the overall architecture of the proposed model, comprising of shared encoder, an ASR decoder, and a VAD branch. We used CTC attention-based streaming transformer ASR, whereas we used a linear layer for the VAD branch. This model uses no external VAD module, and the VAD branch and ASR model share an encoder to minimize the total number of parameters. The model was trained in 2 stages. First, a conventional streaming ASR model is trained using paired data of segmented utterances and the corresponding text sequences. Then the VAD branch is trained while freezing the pre-trained ASR model using unsegmented long recordings. Let me explain the detail about the VAD branch and how to use it during decoding in the next page. The VAD branch output the probability of the presence of a voice segment using the hidden state sequences. Then frame-wise posterior probabilities of the voice activities are estimated using a fully connected layer with a sigmoid function. The VAD branch estimates a sequence of voice activities depending on the voice activity probabilities. If a posterior probability is above a certain threshold, those segments are regarded as voice segments. Additionally, we introduced the consecutive non-voice segments threshold V to prevent detection of short non-voice segments like this. If the number of consecutive non-voice segments exceeds V, those segments are considered as non-voice. When non-voice segments are detected, the encoder-decoder history is reset. In the streaming transformer, hidden state sequences are processed blockwisely. Since the duration of a single block is about 1 to 2 seconds, it may not be possible to properly segment an utterance if the hidden state sequence is simply divided by blocks. In this figure, the left block contains 4 consecutive non-voice segments as shown in yellow. However, since the left block contains part of the beginning of the next utterance, a simple segmentation by predetermined block would result in the split in the middle that would break the context in the next utterance. Therefore, the hidden states block is resized at the center of the detected non-voice segments before transmission to the ASR decoder. We call this operation reblocking. To validate the 3 contributions described, we evaluate the proposed method with respect to the impact on ASR and its computation time. Firstly, we compare the proposed method with the conventional approach. Then, we confirm that the reblocking technique improves the performance by calculating the CER and WER. Finally, we verify the proposed method reduces the computational cost by calculating the real-time factor. We compare the proposed method with 2 baselines. The one is that the speech input was automatically divided when the length of the hidden state exceeds the length threshold of hidden state sequence L. In other words, the speech input was automatically divided at equal time intervals, regardless of voice activities. Second one is CTC-based method, which I explained in the related work. The speech was automatically segmented based on the blank labels. This table shows CER and WER results by evaluation sets. At baseline, CER was smallest when L equals to 300. The proposed method showed comparable or better CER than the baselines. While the baseline divides the speech input at equal intervals, L, regardless of voice activities, the proposed method improves CER by segmenting it at appropriate non-voice segments. The proposed method also showed 50% CER reduction compared to the CTC-based method. In summary, we obtained better results than the baselines. Then we evaluate the effect of reblocking technique. This table shows the comparison between with or without reblocking. The speech input was automatically segmented using the VAD branch for both with and without reblocking. But the only difference is that if the hidden states block were reblocked or not. As you can see in the table, obviously the reblocking technique improved the performance. These figures shows the difference between with or without reblocking. While the hidden state blocks were not appropriately divided without reblocking, reblocking technique properly segmented each utterance. Therefore, we confirmed that the proposed reblocking technique is effective for block-based streaming ASR. Finally, we measured real-time factors. This table shows the CERs and RTFs for different consecutive non-voice segments threshold B in the proposed method. When B equals to 10, the proposed method shows the best performance in terms of CER, achieving a smaller real-time factor than the baseline. because the proposed method discards non-voice segments. The real-time factor is reduced by resetting long hidden state history when VAD branch detects non-voice segments. Therefore, the proposed method reduced the real-time factor by 27.3%, achieving better CERs than the baseline. We proposed a model that integrates VAD branch into a block processing-based streaming ASR system and a reblocking technique to avoid inappropriate segmentation of the speech input. Experimental results showed that the proposed method improved the CER with 27.3% reduction in real-time factor compared to the baseline. Thank you for watching this video.